Towards the end of the last subsection, I asked you to try to set up a couple of problems using Avogadro's number as a conversion factor. There, I promised that I would explain it. Since I promised, here you go. Our first problem asked us to determine the number of particles in a 2-mole sample. It doesn't say a sample of what, but that isn't important because of the definition of the mole. There's always going to be the same number of particles in 1 mole of whatever, regardless of what that whatever. We're always going to begin our calculations with our given quantity. In this case, that's that 2 moles listed in the problem. Our next step is to identify what we're asked for, which is to find the number of particles in this sample. And our third step is to determine the path we need to take to move from moles to particles, which is to use Avogadro's number. Now, one of the biggest hurdles for students new to dimensional analysis is where do you start? And again, always start with the given value. Lots of times you'll be given a value and a conversion factor in your problem, which you can differentiate by the units. In those cases, you'll begin with a value that has a single unit associated with it and save that value that has more than one unit associated with it so it can serve as a conversion factor later, at least until we get to those limiting reactant problems. Now notice also that I wrote down both the value and the unit. This will help me keep track of where I need to proceed as my calculation gets going. Now, all that said, it's time to move away from the moles unit in this problem using that conversion factor. Since the mole is in the numerator here, it's going to need to appear in the denominator in my next step so that my units can cancel. Think back to Algebra 1 where you canceled x. And since Avogadro's number is a definition in terms of 1 mole, that's what has to go in this denominator spot. This will allow the moles units to cancel across that division bar. All that's left is for me to add the rest of the definition for Avogadro's number using particles as my unit. Now to complete the calculation, multiply the values in the numerator together. Separately, multiply the values in the denominator together. Yes, it's a 1. Then divide the resulting products. The result is 1.20 times 10 to the 24th particles in our 2-mole sample. Now, your last step in any calculation this term or next should be to think about whether your answer makes sense. Here, you should just be doubling Avogadro's number, and this value corresponds with that action. The second one requires a very similar thought process despite requiring us to move in the opposite direction. Again, begin with your given value, which is 7.91 times 10 to the 23rd particles. We're working away from particles and towards the mole, so we will need to place Avogadro's number to cancel particles and facilitate this. Remember that the definition is the number of particles in 1 mole, so Avogadro's number will need to be added to our calculation in a way that agrees with this statement. This leaves us with a value of 1.31 moles. Now again, double check that your answer even makes sense. The given value is larger than a mole by about 1/3. So an answer of 1 and about 1/3 makes sense. A goodly number of you ended up with the same coefficient than I did, but a different exponent in that first example. Now, if this is the case, you likely just used your calculator incorrectly. It's pretty common, so common that it needed to end up in this video. Now, a number in scientific notation is in fact just a number, so it needs to be entered like any other number might be entered, even if it appears more complicated. Most students use the caret button, which is the thing that looks like a rooftop. But when you do that, instead of telling your calculator, this is just a value, you're telling your calculator to carry out a calculation. Instead of raising a value to a power, which is what that caret button does, use your calculator's exponent button to signify that you're entering a value. If you happen to have this version of the TI-30, and the majority of you probably do, you'll need to look for the EE button found just north of the 7. Since it's written above the button itself, it's actually a second function and will require you first press the second key. So your keystrokes to enter Avogadro's number would be 6.022, the second key, then press that EE, then type in 23. This tells the calculator that it now has a value in scientific notation to deal with. Now, I'd love to tell you that all TI models handle scientific notation with the same keystrokes, but that's just not the case. The TI-36, this other version of the TI-30, and the fancier TI-89, for example, includes the exponent as a primary function, so the second key is not necessary. If you upgrade from that 30 level, which is unnecessary for this class, but you probably also have to take calculus, to this fairly common TI-84 or this fancier version of the same calculator, the exponent, or EE, will be found above the 7 again. So you'll have to go back to using that second function. Upgrade even more to the nspire, which I wouldn't actually recommend unless you're a math major or maybe an engineering major, and you don't have an exponent key at all. You'll just use a cursor to enter your exponents. Then a handful of you guys will have Casio calculators. My favorite calculator is an older model Casio, so these will work great for this class. They do give their exponent button a different format though. On this model, there's no need for a second key. There's a much less variation between the Casio models in terms of placement. My older model puts the button in the same place, but it labels it EXP instead of the time 10 to the X like this one does.